Welcome back. In this unit we delve into the world of recurrent neural networks, or RNNs. These powerful networks are specifically designed for sequential data, making them invaluable for tasks like machine translation, speech recognition, and more. Let's study how RNNs work, their challenges, and the solutions they offer. First, let's consider an example of sequential data. Such data can vary in length. They have data points that depend on previous ones, and they have repeating elements and patterns. While feed-forward neural networks excel at static data, they fail when modeling sequential data, because they cannot remember previous states. In contrast, RNNs overcome this limitation with their memory capabilities, allowing them to effectively understand and process various types of sequential data, such as text and time series information. Let's explore how RNNs achieve this memory functionality. A recurrent neural network, RNN, includes at least one recurrent layer, where each neuron has two inputs and two outputs. One output functions like a typical feed-forward network output, while the other loops back to the neuron's input. This setup ensures that in addition to the current steps input, the neuron also receives the output from the previous step as input. This structure endows the RNN with a hidden state, enabling it to retain memory of past steps. The recurrent nature of RNNs results in large gradients for weights greater than 1 and tiny gradients for those smaller than 1, leading to either overly large or minuscule steps when minimizing the cost function. Managing this issue can be aided by hyperparameter tuning and reducing the number of hidden layers. Additionally, RNNs are limited to retaining information from the preceding step only, which is inadequate for contexts spanning multiple time steps. Long short-term memory, LSTM, is a variant of RNN architecture, introduced by Hochberger and Schmidhuber in 1997. Specifically devised to tackle the challenges of vanishing gradients and exploding gradients and long-term dependencies. Similar to the normal RNN, the LSTM unit takes the current step's input and the previous step's output as inputs, but its architecture is more complicated. It incorporates a dedicated cell state designed to retain information across multiple steps and 3 distinct gates to regulate the flow of information. First, the forget gate determines what portion of the cell state to retain or discard based on inputs from the current step and the short-term memory. Second, the input gate decides what percentage should be stored in the cell state. And third, the output gate, receiving inputs from the cell state, short-term memory, and current step, governs the generation of the output value or the updated short-term memory. This process iterates similarly to traditional RNNs. The absence of weights in the cell state contributes to more stable gradients compared to those in a regular RNN. Today we explored how RNNs utilize past outputs as inputs to capture the sequential data patterns. Challenges such as vanishing or exploding gradients and the absence of long-term memory hinder its practical implementation. However, more advanced models like LSTM address these issues, enhancing RNN's real-world performance. These techniques find applications across diverse domains, including time series forecasting and language processing. See you in the next unit.